We start with oblique collisions and what you need to know. Number 1, you need to know the formula for principle of conservation of momentum and Newton's elastic law. The m's are the mass of the first and second sphere, respectively u1 and u2, initial velocities before the collision of the first and the second sphere, v1 and v2, velocities of the spheres after the collision. E then is the coefficient of restitution, is always a value between 0 and 1. Okay, the next thing you need to know is if you draw a line between the centers of the spheres, whatever direction that's in, that's the component that changes. The perpendicular component to that doesn't change at all. So in that case, the line is horizontal, that's in the I direction, the I component changes, the J component doesn't. Second one, in this case the line joining the centers is a vertical line, it's in the J direction, so the J component changes and the I direction stays the same. And the third option is somewhere in between. And for this one, what I'd suggest is rotating the plane so that either the line joining the centers is horizontal, as in the I direction, so the I component changes, the J stays the same, or you could rotate it so that the line joining the centers is vertical, and then it would be like the middle example there. Okay, other things you should know. Speed is the magnitude of the vector. So to calculate the speed, it would be the square root of the number in front of the I component squared plus the number in front of the J component squared. So square root of I squared plus J squared. The next one is the impulse, and the impulse is the change in momentum. We always take the positive value of it. So the impulse is going to be the mass of one sphere multiplied by its velocity after the collision, minus the mass of the same sphere multiplied by the same sphere's velocity before the collision. And also there is some formula with kinetic energy, and here's where it gets tricky. So we know kinetic energy is a half mv squared. If there are two spheres colliding, for the change in kinetic energy, you'll have 4 formula. You'll have the kinetic energy of the first sphere before the collision plus the kinetic energy of the second sphere before the collision. You'll also have the kinetic energy of the first and the second after the collision, and you'll be subtracting the kinetic energies before from the kinetic energies after. Actually the other way around, but yeah, subtracting the ones after from the ones before. The fractional change in kinetic energy is the change in kinetic energy, which is calculated from the step above, divided by the kinetic energy before. And remember, the kinetic energy before is a half m1u1 squared plus a half m2u2 squared. And then finally, the percentage change in kinetic energy is the step above again, so it's the fractional change in kinetic energy just multiplied by 100 over 1. You're basically just converting a fraction to a percentage, and you do that by multiplying by 100. Okay, other stuff you should know. Tan A is equal to the J component over the I component. So this only works when the angle is the angle between the vector and the horizontal direction. That's really important. So between the I-axis and the direction the vector is in, that angle there can be found with tan of the angle is equal to the J component over the I component. This is what I mean. So if we look at the diagram, the angle there is between the vector and the horizontal line, and to find that angle, we pretend we don't know it, is equal to the J component over the I component. Now, very important that we take positive values in all cases. So when the angle is like that, the I and the J component are positive, and you can just fill in the I and the J component and it works out. But if you're given something like this, so I'm looking at the top vector there in that new diagram, so that's the one going to the top left. In that case, you have a positive J and a negative I. So what I would do here is I would change the negative I to a positive I, just by swapping the signs, and then I can use tan of A is equal to J over that positive I component. That then would give me the angle between that vector and the horizontal line. Now, what we'll come across later is if you're looking for an angle between the vertical and the particular vector, then to calculate the tan of the angle, it would actually be the I over the J, but we'll see that at a later video. Okay, setting up questions. So for me, what I need to do is fill in a table. So if we have something like that, or something like that, it doesn't matter. We still need a table. And the table will be the two spheres A and B. What you'll have is an initial velocity vector with an I and a j component. You'll have a mass, and you'll have a final velocity or a velocity after the collision in terms of I and j. The thing to remember here, I've said it already, for the first diagram, the line joining the centres is horizontal, so the I component changes and the j component stays the same. For the middle diagram, the line joining the centres is vertical, so the j component changes and the I component stays the same. And for the third one, I would rotate the plane. Personally, I'd rotate it so that the I components are horizontal, and then so that the line joining the centres is horizontal, so then the I component changes and the j component stays the same. Once you have that, you can get the unknown values for whichever components you're looking for, and then you can solve additional questions. All right, you would use those two formulae with the component that changes, subbing them into those equations, and then you get your values for the unknown velocities.